In this video, we're going to dig a little bit deeper into the topic of antiderivatives. As we do that, we're going to address the final 3 learning goals. We're going to begin with a definition here. In the last video, we talked about how functions could be related as one being an antiderivative to the other. We never really established a formal notation, though, to connect the two. And so that's what we're going to do here. So if big f of x is an antiderivative of f of x, then we can write it this way. This symbol here is an integral sign. It was introduced by Gottfried Leibniz, one of the creators of calculus. And so what this is saying is these two functions are linked, where this one is the antiderivative to f of x, or if you wanted to look at the relationship the other way, this one is the derivative of big F of x. And so this is now giving us a notation where we can establish the relationship between these two things all within one line. So on the right hand side I have the general antiderivative. On the left hand side I have the function it's the antiderivative of. The thing on the left hand side we have a specific name for. We refer to it as the indefinite integral. And so that's the new definition here. The indefinite integral of a function defines this family of antiderivatives that we have on the right. And I refer to it as a family because, again, this is the general antiderivative. And so what that means is that there's infinitely many options for what that constant c could be. So it is actually not just one antiderivative, but a whole family of them. And so this notation is, again, connecting these two functions, a function to its antiderivative or a function to its derivative, depending on which way you look at the relationship. Now, I always find that at the high school level, sometimes seeing theorems and definitions in a mathematical context makes an idea look more intimidating than it actually is. So we're going to look at this through some examples and see if we can't wrap our heads around it that way. So in this first one, I'm saying I want to find the general antiderivative of this function, f of x equals x squared plus 4x minus 5. So now that we've established a notation, I'm going to write that rule we established from the definition on the last slide. But then I'm recognizing I have my function f of x here, so I could actually substitute it in to the indefinite integral. So I'll have x squared plus 4x minus 5 here. And what this is going to be equal to on the other side of the equal sign, I'm going to be able to write out the antiderivative of that function. So this is a polynomial function with 3 terms. In the same way that when I differentiate, I go term by term and do it individually, we're going to do the same thing when we find an antiderivative here. So I'm going to look at that first term, x squared, the function that would have come before that. The exponent would have to have been 1 higher, and I will have to divide by that new exponent. And then when I move on to the next term, it's going to be 4x. The exponent's going to go up by 1 to a squared, and I'm going to divide by that new exponent. And we'll simplify here in a second. The minus 5, if it's a constant that I have now in the function that preceded it before we took the derivative, it would have had to have been minus 5x. And then finally, because I'm going for a general antiderivative, I'm going to have to add a plus c to the end. And so I can do a little bit of tidying here of my terms. That second term with the x squared, I can actually simplify in the coefficient. So I have plus 4 over 2, so it's just going to be 2x squared when I have it all simplified. And so that's the general antiderivative of the function that I started with. So we could say that this is big F of x. If we wanted to label our final answer that way, we wouldn't have to. The indefinite integral is sufficient there to communicate that. But this function is the function that if you took its derivative, you would get x squared plus 4x minus 5, right? And so that's what an antiderivative is. It's the function where when you take its derivative, you're going to get this one. Let's go ahead and take a look at another example then. This one I wrote out in Leibniz notation just to mix it up again. And I've also expressed this function using trig functions so that we could do something a little bit different than a polynomial function. So when I go to write this in integral notation, I will still kind of take that same approach of the indefinite integral of f of x is equal to big F of x plus c, but I'll write it a little bit differently here. Leibniz notation was actually designed to be converted into integral notation. And so if I rewrite the function like this, move the dx over to the other side, you can actually start to see why in the general definition we write a dx there. It's actually based on Leibniz notation. The idea is if I integrate on the left side, so I do the indefinite integral and find the antiderivative of dy, it's just y. And so my original function y is going to be the indefinite integral of the right-hand side, and that's where that rule comes from initially. So here I'm going to do the indefinite integral. Coefficients don't matter when I'm integrating in the sense that they don't change what's happening with the integration. I just need to focus on the fact that there's a cos x there, and I know that the function that would have come before that would have been a sine x. With my second term, sine x, the function that would have come before that would have been a negative cos x. And then to make it a proper general antiderivative, I just have to add a constant at the end. I don't have to say what that constant is, I just have to put it there so that it's a general antiderivative. And so here, again, we've just established a new notation that's allowing us to work backwards from essentially a derivative to the original function. So where this gets really interesting is where we're going to take it next, and actually defining an explicit function and figuring out what that value for c is. So here in our third example, I'm actually extending this a little bit further. I'm going to want to find the function f of x given the second derivative, and I know some information about the original function. So I know that f of 0 is 9 and f of 2 is 15. This is actually pretty common in an application scenario where we might be able to find a model for the second derivative, whatever that quantity represents, and we might know some initial conditions about a situation, and then we can use that to work backwards to find an overall model. So we're going to take a few steps here. First of all, we need to recognize that if I want to work backwards to f of x, then I'm going to have to do the indefinite integral of its derivative, right? That's how we'll work our way back up to the antiderivative. But I don't have the first derivative, and so I need to think again about this relationship we've established between functions and derivatives, or functions and their antiderivatives. And in order to work back to the first derivative, I'll actually have to do the indefinite integral of the second derivative. So I've crafted this problem so that we will have to find the indefinite integral twice. We're going to have to work backwards through our differentiation rules 2 times to get back to the original function f of x. So let's take a look at what that looks like. We'll do our first step is find f prime. So we'll work back incrementally. So to find f prime, I've already said I'm going to do the indefinite integral for 2 minus 12x. That's the second derivative. And if I work backwards from that, the antiderivative for 2 is just going to be 2x, and the antiderivative for 12 will be minus 12x squared over 2, which can simplify to be 2x and then minus 6x squared. And I suppose I should put a plus c there on the end, shouldn't I? Because I'm looking for general antiderivatives here. And so here, now I have f prime. That's what this is. And if I take the indefinite integral again, so find the antiderivative of all of those terms, it's going to get me back to the original function, f of x. So that's what I'm going to do now. I'm going to find f of x. And so f of x will be equal to the indefinite integral of f prime of x. And so now I need to work backwards from that function, the indefinite integral of 2x minus 6x squared plus c. And again, I'm going to go term by term here. And so the antiderivative of 2x, the exponent's going to go up, become a 2, and I'm going to divide by 2, so the antiderivative there is actually just x squared. And then if I do the antiderivative of minus 6x squared, I'll end up with minus 6x cubed, and I divide by that new exponent of 3, and that's going to simplify nicely in a second. And when I go to do the antiderivative of plus c, now I don't know the actual value of c, but I do know it's a constant. And so if I'm taking the antiderivative of a constant, I know what would have come before it would have been a linear term. So I'm going to write this as cx, because that would have been the term that came before. And then, again, because I'm aiming for a general antiderivative here, I am going to have to add another constant at the end. So I'm just going to use the next letter, plus d. And so this is a very general version of f of x. This is a general antiderivative. However, in this particular instance, because I've been given some initial conditions, I don't have to actually stop there. I can go a little bit further and figure out those values of c and d. Because I know 2 points on the function f of x, I could substitute the values in for those 2 points and solve for my 2 unknown values. And so that's what I'm going to do here. So I know that f of x is equal to x squared minus 2x cubed plus cx plus d. So I just simplified the coefficients there and tidied up the terms. You might have rewritten it with the cube term first, which would technically be the proper order. We could like to go in descending order of exponents. And so here I'm going to end up subbing in numbers, so it really won't matter in the long run. This is my function f of x. I know that f of 0 is equal to 9. If I plug 0 in for x, I'm going to lose out on this term, and this term, and the only thing that's going to be left is d. So it looks like d is equal to 9. So I was able to solve for that one pretty quickly. So now I can use the other piece of information I know, that f of 2 is equal to 15, and sub that in here, and hopefully be able to solve for c. I say hopefully, but I know I'm going to be able to. So I've replaced d with 9. I'm not going to leave it in there as a d because I know what it is. I can skip past that. I don't have to leave it as an unknown. And so if I go to simplify this, I end up with 15 is equal to 4 minus 16 plus 2c plus 9. And then it's just a matter of simplifying and gathering all my like terms together. I'm going to move all those numbers over to the left-hand side where they will simplify with that 15 to become an 18. And that will be equal to 2c. So it looks like in this particular instance, c happened to be 9 as well. And so my original function then, f of x, would have been equal to, and here I'll write it in the proper order, minus 2x cubed plus x squared plus 9x plus 9. And so now this is no longer a general antiderivative like it was here. This is actually a very specific antiderivative. It's an explicit function now. There's no uncertainty anymore. I know that based on the information that I was given, that this was the second derivative of the function, and these were 2 points that I knew were on the function. Because I had that information, there's no ambiguity here anymore. There's no need to generalize. I can actually find the specific antiderivative, which is the function that we have here as f of x. So in the grand scheme of things, this is the big skill that we need to work towards mastering, because this is the kind of thing you would use in an application setting where you would collect information, those initial conditions, the 2 points we were given from the start. You would have that, and then you would have a relationship that modeled the rates of change of something, and you would actually integrate backwards to find a relationship that that measured something else entirely. That's actually something you would do pretty often, coming up with models using calculus. And so this is actually the fundamental skill that we should be working towards mastering. It's good if you have a solid grasp of antiderivatives in general, but this is the skill you really want to lock down to make sure that your understanding of calculus is as refined as it can be.